Hello there, and welcome to Just About Earth, where curiosity gets cozy and science settles in for the night. Tonight's gentle journey is one that stretches back so far it almost slips beyond imagination. We're diving into the birth of our world, not a chapter in its story, but the opening line, the moment when Earth, our warm little rock adrift in space, first came into being. Have you ever wondered what came before mountains, before oceans, before even the idea of blue sky and green trees? Imagine looking at your feet and realising the ground beneath you began as fire and stardust. Funny to think that the same planet holding your house, your shoes, your pets, once didn't exist at all. And then, suddenly it did. But before we start building planets out of chaos, I'd love to know, where in the world are you listening from tonight? And what time is it in your little pocket of the universe? If this slow unravelling of ancient mysteries brings you even a whisper of calm, I'd be quietly grateful if you gave the video a like, maybe subscribed, or shared it with someone else who's ready to drift off to science. It helps this calm little corner reach others who need a soft story at the end of a long day. So settle in, slow your thoughts, and let's begin. Because before there were birds or buildings or bedtime stories, there was just dust drifting in silence. And from it, somehow, the Earth was born. About 4.5 billion years ago, give or take a few cosmic blinks, something extraordinary happened in the swirling chaos of a young solar system. A violent ballet of collisions, gravity, and molten rock gave rise to the planet you're lying on right now. The ground we take for granted is older than memory, older than bones, older than time zones or tea kettles. And yet, its story is still unfolding, and we're only just learning how it began. Sometimes, to understand something ancient, you have to notice something strange in the present. In the late 1960s, a group of geologists in Western Australia noticed something odd. Nestled in the dry red heart of the continent were smooth, rounded pebbles embedded in ancient rock. Pebbles that shouldn't have been there. They looked like river stones worn by water, but the rocks around them were nearly 3.5 billion years old. How could there have been rivers back then? Was there even land? Oceans? Could the Earth already have had flowing water while life as we know it hadn't even begun to blink? That little mystery, the shape of a stone, cracked open a much bigger question. One that would take decades of fieldwork, arguments, lab tests, satellite data, and no small amount of mud on boots. What was the early Earth like? What did it feel like to stand on it, if you could? And where exactly did it come from? Fast forward to a laboratory in California. A scientist is studying tiny grains trapped in a piece of zircon, a mineral that forms in molten rock and holds on to secrets like a diary buried in crystal. She carefully analyses the isotopes inside, measuring how uranium decays into lead. It's a kind of atomic clock ticking away not in seconds but in epochs. And from this grain, no larger than a fleck of dust, she finds something astonishing. The Earth was already forming crust, solid ground, just 160 million years after the solar system itself began. That's fast. Cosmically speaking, Earth wasted no time becoming Earth. But we're getting ahead of ourselves. Let's step back for a moment. Picture the solar system before it was a system. No planets, no moons, no quiet revolutions around the sun. Just a vast, spinning cloud of gas and dust. The leftovers of older stars that had lived, burned, exploded, and scattered their ashes across space. This cloud, called a solar nebula, was immense. And slowly, gently, inexorably, gravity began to tug it inward. It spun faster as it collapsed, like a figure skater pulling in her arms, and in the centre, heat built up until hydrogen atoms fused and lit the sun's first fire. Around that newborn star, the leftover material formed a disk. Imagine a vast ring of microscopic grains drifting in spirals like flour caught in a sunbeam. Dust clung to dust, building pebbles. Pebbles clumped into boulders. Boulders smashed together into planetesimals, baby planets, tumbling and crashing through space like cosmic toddlers testing their balance. It wasn't a gentle process. It was loud, hot, violent. But out of that chaos, order slowly emerged. Earth was born not as a gentle marble, but as a glowing sphere of molten rock. Its surface churned with lava and impact after impact. Some the size of mountains, others the size of Mars. Yes, Mars. Because not long after Earth took shape, it had a visitor. A rogue planet, likely the size of our red neighbour, smashed into the early Earth at just the right angle and speed. It didn't destroy the planet. Instead, it sheared off a massive chunk of material, vaporized rock and molten metal that spun out into orbit. And from that debris, the Moon was born. A child of collision, raised by gravity. We know this not just from imagination, but from rock samples. The Moon's composition is eerily similar to Earth's outer layers. Its orbit, its size, even the weird tilt of Earth's axis. All are fingerprints left by that ancient impact. This event, sometimes called the Theia collision, after the mythical mother of the Moon, didn't just create our satellite, it reshaped the Earth. It may have stripped away a heavy early atmosphere, it might have accelerated Earth's spin, and it certainly left behind a glowing molten planet in need of some serious cooling. So how do we know all this? From rocks mostly. Some of the oldest rocks on Earth are found in Canada, Greenland and Australia, places where ancient continental crust pokes out from beneath newer layers like fossils in a library. They whisper stories in isotopes and mineral grains, in oxygen ratios and lead decay. They tell of a world without trees, without animals, without even stable land, a world of fire and storms and endless bombardment from space. And then, suddenly, water. No one knows exactly when or how the oceans appeared. Some think comets, icy bodies from the outer solar system, delivered water in their crashes. Others point to volcanic outgassing, the idea that early Earth's interior was rich in water, and it was slowly exhaled through eruptions, clouds, and eventually rain. Either way, at some point the sky began to darken. The steam cooled, and it rained, and rained, and rained. For millions of years, the early Earth may have been wrapped in storms so vast and unrelenting that the surface became oceanic. Not islands in a sea, but seas with no islands. We're not sure how long this ocean world lasted. Some suggest there were volcanic proto-continents, patches of rock rising above the waves. Others believe the planet was almost entirely submerged, but eventually tectonics began to stir. Plates shifted, continents coalesced, and the Earth, still unrecognizable to us today, began to take form. What makes this all the more remarkable is how much of it we've uncovered from tiny hints. A grain of zircon, a pebble in an old rock bed, a strange wobble in the Moon's orbit. Science doesn't always move in leaps. More often, it steps quietly, squints closely, and listens to the rocks. One such rock was found by a geologist named Harrison Schmitt, the only geologist ever to walk on the Moon. During the Apollo 17 mission, he brought back samples of lunar soil, which helped confirm the Theia impact theory. Back on Earth, researchers noticed something unusual in those samples. They contained pieces of Earth itself, blown into space during the collision and preserved on the Moon, where erosion and tectonics never reached. The Moon, in a way, became a museum of the Earth's forgotten youth. Other clues come from magnetic fields. Deep beneath our feet, Earth has a liquid iron core that spins and churns, creating a magnetic field that shields us from solar wind and cosmic radiation. But that core had to form somehow. As the young Earth cooled, heavy elements like iron and nickel sank to the centre, creating a layered planet. Core, mantle, crust. This process, called differentiation, gave us not just structure, but a magnetic umbrella that protects our atmosphere, and by extension, life. We can even trace the echoes of this formation in meteorites. Certain iron-rich meteorites are believed to come from the shattered cores of early planetesimals that never made it to full planet status. Studying them is like holding a piece of Earth's interior, preserved in space since the dawn of the solar system. And speaking of life, while Earth's formation was violent, it laid the groundwork for everything to come: the creation of a stable crust, the presence of water, the protective magnetic field, the gentle tug of the moon stabilizing Earth's tilt and seasons. All of these were essential ingredients in the slow, improbable recipe for life. None of it was guaranteed. Earth could have been too small to hold an atmosphere. It could have spun too fast or too slow. It might never have been hit by Theia, or could have been hit again and shattered. Yet here we are, 4.5 billion years later, listening to its story. And it all started with dust. Try just for a moment to imagine what Earth looked like before anyone ever looked at it. No trees, no birds, no green, no blue. A world without colour, at least not the kind we associate with calm meadows or painted skies. In those first few 100 million years, the Earth was a world still deciding what kind of planet it wanted to be. It had a surface, yes, but it was raw, blistered and ever-changing, the kind of terrain that seemed to simmer with impatience. Picture molten rock cooling into jagged crusts, only to be broken apart by fresh impacts, new lava flows and endless tectonic shifts. Volcanoes didn't sit quietly in mountain chains. They erupted from cracks in the ground like the planet itself was still exhaling the heat of its birth. The sky wasn't blue, not yet. In fact, it probably wasn't any one colour at all. Some models suggest it might have been red or orange, thick with carbon dioxide and methane, cloaked in volcanic smog, swirling with steam from the still-forming oceans. Imagine standing on a volcanic shoreline, if such a thing could be stood upon, with sulphur in the air and the light of the sun a dim, filtered glow behind churning clouds. And yet, it rained. Not in the way we know it now. No gentle drizzle or afternoon showers. The early Earth's atmosphere was dense and unstable, filled with vapour. When it cooled enough for condensation to happen, it poured. Storm after storm after storm. It might have rained for centuries at a time. Whole epochs defined not by geology, but by weather. Beneath those endless clouds, oceans began to form. Salty, yes, but not in the way you'd expect. They were acidic, rich in dissolved minerals leached from the young crust, stirred by tides from the newly formed moon and waves from constant asteroid impacts. If the planet ever calmed, it didn't stay calm for long. And below the waves, something extraordinary was happening. Deep beneath the surface, where light couldn't reach and pressure was immense, the planet's heat bubbled up through hydrothermal vents, cracks in the seafloor where hot, mineral-rich water gushed into the ocean. It's here, many scientists believe, that the first whispers of life may have stirred. Not with a bang, but with chemistry. Simple molecules reacting with metals, temperature and time, slowly forming more complex chains, eventually something that could replicate, and from that, everything else. But even before life, the Earth was already dancing through a kind of restless transformation. Plate tectonics had begun, maybe not exactly as they work today, but the idea was there. Massive slabs of crust drifting atop the pliable mantle, colliding, diving beneath each other, cracking open new oceans and crushing continents into mountains. And with this movement came change. Islands formed and sank. New minerals surfaced. Gases were released or absorbed. Every crack and shift rewrote the atmosphere and ocean chemistry just slightly, and the planet kept cooling, slowly, steadily, reluctantly, inching away from its molten beginnings towards something more stable. Some of the earliest rocks that survive today come from this time, though they are rare and weathered like memories almost forgotten. The Acasta gneiss, found in Canada, dates back over 4 billion years. It's not just old, it's a time capsule. A piece of crust that somehow avoided being melted, crushed or recycled in the great tectonic churn of the Earth. When geologists hold it, they're holding the crustal memory of a planet that had just learned how to be solid. Not far behind in age are the zircons, tiny crystals found in the Jack Hills of Western Australia. Older than any rock, they formed in molten environments and survived billions of years embedded in younger stone. From their isotopes, we've learned that liquid water may have existed on Earth just 150 million years after it formed. That's shockingly early, astonishingly lucky. But luck, in science, often just means the right conditions persisted. And Earth, despite its violent youth, had a few key ingredients that helped it hold on to those conditions. For one, its size. Not too small like Mars, which lost most of its atmosphere, and not too large, like gas giants, which never even formed solid surfaces. Earth was just right. Big enough to retain an atmosphere, small enough not to become a star. It had a molten iron core, creating a magnetic field strong enough to deflect solar wind and shield the young atmosphere from being stripped away. Then there was the Moon, born of chaos but essential to stability. Its gravitational pull slowed Earth's rotation and kept the planet's axis from wobbling wildly. That stability meant consistent seasons, which would eventually matter very much to life. And there was the distance from the sun, not too hot, not too cold. This so-called Goldilocks zone is often romanticised, but it's crucial. It allowed liquid water to exist, not boiling off, not freezing solid. Water, that slippery, shape-shifting molecule, was the Earth's first great sculptor, carving valleys, dissolving minerals, transporting nutrients, and maybe, just maybe, coaxing the first spark of life into being. At some point, we don't know exactly when, the Earth transitioned from a world of chemistry to a world of biology. The first cells likely formed in those deep-sea vents, or in warm, mineral-rich pools on the surface. They were simple, no nuclei, no organelles, but they could replicate, they could evolve, they could in a very primitive sense live. The world they inhabited was still alien to us. The oceans were greenish and murky, filled with dissolved iron. The sky, still lacking oxygen, held no ozone layer, allowing dangerous radiation to reach the surface. Life clung to shadows, to depths, to sheltered places. It didn't yet breathe in the way we do. Oxygen was toxic, a byproduct to be avoided. And yet, life endured. Stromatolites, layered structures built by microbial mats, began to appear. They're still around today, in a few remote places, like Shark Bay in Australia. But their ancestors were pioneers, capturing sunlight in a primitive form of photosynthesis, and slowly, over eons, releasing oxygen into the atmosphere. They didn't mean to change the world, but they did. It would take hundreds of millions of years for that oxygen to accumulate. At first it rusted the oceans, turning dissolved iron into solid oxides that sank to the seafloor. We see the evidence in banded iron formations, striking red and black layers in ancient rock that tell of oceans bleeding rust. Only after the oceans had soaked up enough oxygen did it begin to build in the atmosphere. And when it did, it triggered one of the greatest transformations in Earth's history, the Great Oxygenation event. But that's another story for another night. For now, let's linger a little longer in this ancient world, a world that hadn't yet heard thunder or birdsong or the crunch of leaves underfoot, a world of simmering oceans and restless crust, of chemical whispers and volcanic roars, a place where the sky was strange, the air unbreathable, the land barely land at all. And yet, the Earth was already beautiful. Not in the way we think of beauty, not soft sunlight or blooming flowers, but in its rawness, its honesty, its power. This was a world still becoming, still inventing itself, and we are its children. Every cell in our bodies carries traces of that early world, elements forged in stars, minerals birthed in lava, water older than the moon. We are the descendants not just of life, but of the planet itself, shaped by it, sustained by it. And in quiet moments, when we listen closely, we can almost hear it still. The sigh of ancient oceans, the hum of shifting plates, the slow, deep pulse of a planet that has been alive in its own way since before life began. Change on Earth has rarely arrived politely. It doesn't knock, it doesn't wait. It explodes, it crashes, it overwhelms, sometimes in minutes, sometimes over millennia. But the planet changes, and it always has, and perhaps no change was more dramatic, more sweeping, or more quietly lethal than the arrival of a gas we now call life-giving, oxygen. If you stepped outside today and took a breath, you'd be inhaling about 21% oxygen. It's what fuels our cells, feeds our brains, and lets fires burn. But in the early Earth story, oxygen was a newcomer and a troublemaker. Before it arrived, the planet's atmosphere was rich in methane, carbon dioxide, water vapour, and traces of ammonia and hydrogen. It was a cocktail suited to a world without complex life, and many early microbes had adapted beautifully to it. They thrived in low-oxygen environments, deep in the ocean or in shallow microbial mats. They were anaerobic, living without oxygen and often poisoned by it. Then came photosynthesis, not the kind we learn about in school with leafy green plants and smiling sun icons, but a far simpler version, practiced by ancient bacteria, most likely cyanobacteria, sometimes called blue-green algae, though they're not actually algae at all. These microbes floated in shallow seas, soaking in sunlight and using it to convert carbon dioxide and water into energy. And as a byproduct, they released oxygen. At first, that oxygen didn't go far. It reacted quickly with dissolved iron in the oceans, forming iron oxide, rust, which settled into sediments. Layer upon layer, year after year, rust fell to the seafloor, eventually forming banded iron formations that still decorate ancient cliffs in places like Australia and South Africa. They're geological fingerprints of a world quietly changing, one molecule at a time. But rust has a limit. After a while, there wasn't enough dissolved iron left in the oceans to soak up the oxygen. And so, it began to accumulate, first in the oceans, then leaking into the atmosphere. A slow leak at first, cautious, tentative, but relentless. Scientists call this event the Great Oxygenation Event, or GOE. It began around 2.4 billion years ago, though the timeline is still debated, as are the reasons for its sudden rise. Some think tectonic activity reduced volcanic gas emissions that previously consumed free oxygen. Others suggest the rise of continents allowed more shallow water environments where photosynthetic microbes could bloom. Whatever the cause, the effect was profound. Oxygen spread, and as it did, it triggered a silent apocalypse. For anaerobic microbes, oxygen was toxic. It damaged their proteins, broke apart their DNA, destroyed their cellular structures. Entire ecosystems vanished. Vast mats of microbial life, once dominant across the planet, died out or retreated into deep sediments, hot springs, or places still untouched by oxygen. It was, in a real sense, Earth's first mass extinction. But extinction and innovation often share the same breath, because while oxygen was lethal to some, it was miraculous for others. Oxygen allows for far more efficient energy production. With it, cells could generate more ATP, the chemical energy currency of life, per molecule of food. This surplus would eventually allow life to grow larger, more complex, more adventurous. But not immediately. In fact, after the GOE, the Earth may have entered one of its coldest, bleakest chapters. With methane levels plummeting and carbon dioxide altered by new chemical reactions, greenhouse gases dropped. Sunlight reflected off the still-forming continents. Ice spread. Some scientists believe Earth may have entered its first Snowball Earth state, a near global glaciation where ice reached all the way to the equator. Life didn't vanish, but it went quiet again, slow, hidden beneath the ice or near geothermal vents, waiting. And yet from this frozen pause, Earth would emerge, colder, yes, but clearer. The oxygen persisted, and eventually the skies began to change colour. Before the GOE, the sky may have been tinted orange or even pink, a haze created by methane and other organic gases. But as oxygen accumulated, the atmosphere began to form ozone, O3, a molecule made of 3 oxygen atoms. This ozone formed a layer high above the surface, shielding Earth from ultraviolet radiation for the first time. It was a planetary sunscreen, allowing life to inch closer to the surface, to shallower waters, to light. It's strange to think of a gas as a trigger, not an impact, not a volcano, not a mountain-shattering event, just a molecule, invisible, passive. But oxygen didn't just change biology. It changed the chemistry of oceans, the colour of rocks, the shape of continents. It set the stage for everything that came after. Animals, forests, humans, cities, a planetary reset disguised as air. And it wouldn't be the last time Earth reinvented itself. Of course, not all changes came in gas form. Some arrived roaring from below. About 252 million years ago, still billions of years after oxygen's dramatic debut, the Earth experienced another kind of transformation. Not slow, not invisible, but fire and ash and fury. This was the time of the Great Dying. It began in what's now Siberia, where a massive volcanic event erupted over an area larger than Western Europe. For hundreds of thousands of years, lava poured across the land in waves hundreds of meters thick. This wasn't a single volcanic explosion. It was a province, the Siberian Traps, releasing carbon dioxide, methane, sulfur dioxide, and other gases into the air for millennia. The result? Chaos. Temperatures soared, oceans acidified, anoxic zones, areas with no oxygen spread through the seas, food chains collapsed. More than 90% of marine species went extinct, along with 70% of land species. Forests died, insects vanished, coral reefs disappeared. For a time, Earth was nearly uninhabitable, and yet, even this was part of the planet's long memory of change. We find evidence of this event in ash beds and charcoal layers, in fossil records that go quiet, in sudden shifts in carbon isotopes. And we piece it together with the help of scientists like Elizabeth Kolber, who have traced the fingerprints of extinction across deep time, linking volcanic pulses to biotic collapses. We understand now that extinction isn't always a single strike. Sometimes it's a chain reaction, a cascade. Warming leads to melting. Melting releases methane. Methane causes more warming. Fish die, microbes bloom, oxygen disappears, layers upon layers of effect. The planet doesn't change in one way. It changes in many, all at once, and even as Earth suffers, it survives. Because from the ashes of the Permian extinction rose new life. The ancestors of dinosaurs, the first mammals, the beginnings of coral reefs as we know them. Change is cruel, but it is also creative, and so Earth moves forward, always. Later, about 66 million years ago, another event would shake the world. This one didn't come from within, but from above. A rock, maybe 10 kilometers across, travelling faster than sound, slammed into what's now the Yucatan Peninsula. The impact released energy equivalent to billions of atomic bombs. It vaporized everything nearby. It ignited global wildfires. It sent dust and sulfur into the sky, blotting out the sun. Photosynthesis stalled. Temperatures plummeted. Food webs collapsed. The dinosaurs, once rulers of land, sea and air, did not survive. But mammals did. And among their distant descendants, eventually, would come those strange creatures who split atoms, build telescopes, and tell bedtime stories about ancient rocks and silent oceans. We're still discovering the details of that impact, from the shocked quartz found in global rock layers to the iridium-rich clay that lines the boundary between the Cretaceous and Paleogene periods. We even have a candidate for the actual crater, Chicxulub, a buried scar beneath Mexico, its shape visible from space, its effect still echoing in the fossil record. Each of these events, oxygenation, volcanism, impact, was a different kind of trigger. Each changed the course of life. Each left scars that became stories. And each reminds us that Earth's history isn't a smooth timeline, but a symphony of catastrophes and recoveries. The planet doesn't simply age, it reinvents again and again. And always, somewhere, something survives. A cell, a spore, a seed buried in ash. Earth teaches us that even the worst of days can be beginnings in disguise. Change never arrives alone. It comes with echoes, aftershocks, dominoes tipped in directions no one could quite predict. One shift sets off another, and another, until the world that was becomes the world that is, often without ever announcing the moment it crossed over. So when oxygen rose, it didn't just disrupt microbes or rust the seas, it reshaped the very chemistry of the planet. Iron, once a dominant presence in the ocean, vanished into sediments. Sulfur cycles altered. Methane, one of Earth's earliest and strongest greenhouse gases, was broken down in the atmosphere by oxygen and ultraviolet light. And as methane fell, the temperature followed. The greenhouse blanket that once wrapped the young planet thinned. Heat escaped. The Earth cooled, and then, dramatically, it froze. This was no ordinary winter. This was Snowball Earth. Around 720 million years ago, ice began creeping from the poles. It advanced not slowly like today's glaciers, but rapidly, covering oceans, burying continents. Within a few million years, which geologically is the blink of an eye, the planet may have been encased in ice from pole to pole. Tropical seas, frozen. Equatorial waters, sealed beneath meters of snow. The surface of the Earth became pale, reflective, silent. From orbit, it might have looked like a pearl, smooth, unbroken, and utterly still. But below that icy shell, life clung on, in cracks in the ice, around hydrothermal vents, buried in sediments, extremophiles, the champions of persistence, continued their slow chemistry. Not thriving, perhaps, but surviving. They had no choice, and above them, in the thin layer of ocean still liquid beneath the ice, gases trapped from earlier ages formed a strange pressurized soup. Carbon dioxide, still emitted from volcanoes, built up slowly, unable to escape. And with each passing century, pressure mounted, a silent carbon countdown. Until, eventually, the tipping point arrived. Greenhouse gases broke through the cold, and the world thawed. But not gently. Temperatures skyrocketed, glaciers melted, oceans surged. Weather patterns, if you could call them that, snapped back into motion with force. Storms tore through the atmosphere, coastlines were redefined, and once more, Earth was transformed. This cycle of freeze and flood didn't just rearrange the map, it stirred the pot of evolution. In the aftermath, life rebounded, not only in number but in complexity. Multicellular organisms, long confined to small, soft-bodied experiments, began to diversify. New body plans, new behaviours, new possibilities. Some scientists believe these ice ages acted like evolutionary bottlenecks, squeezing life through narrow corridors where only the most adaptable could pass. And on the other side, evolution exploded into new forms. It wouldn't be the last time catastrophe gave birth to creativity. Fast forward to the Permian extinction, the so-called Great Dying, and you see a similar chain reaction. Volcanic eruptions in Siberia release staggering amounts of carbon dioxide, warming the planet by several degrees. Warmer oceans held less oxygen. Marine animals suffocated. Acid rain from sulfur dioxide devastated forests. Methane, once locked in frozen clathrates beneath the ocean floor, was released, triggering even more warming. It was a loop, a runaway system. Like a pot boiling over, again and again, with no hand left to turn down the heat. The fossil record in this period doesn't show a slow decline, it shows a cliff. Corals vanish. Trilobites, who had survived for hundreds of millions of years, disappear. Insect diversity collapses, and on land, amphibians and reptiles drop away, leaving behind only a few lineages that would eventually give rise to the age of dinosaurs. And in every layer of this story, the culprits repeat: carbon, sulfur, methane, heat, time. They're not villains exactly. They're parts of Earth's machinery. But sometimes, when one gear turns too fast, the whole engine rattles. The same is true for the asteroid that ended the reign of the dinosaurs. It wasn't just the impact that caused extinction, it was what followed. Dust, ash, and vaporized rock filled the atmosphere, blocking sunlight. Plants stopped photosynthesizing. Temperatures plunged. The food chain, starting with the smallest algae, faltered. Herbivores starved. Carnivores followed. Wildfires, ignited by re-entering ejecta, turned vast forests to smoke and carbon. And perhaps most dramatically, the oceans, already reeling, acidified rapidly. The same gases that darkened the sky fell as acid rain, changing the pH of the water, dissolving shells, disrupting reproduction, altering ecosystems at every level. Recovery took millions of years, and yet life found a way forward. After each extinction, the Earth doesn't reset. It doesn't start over. It builds on what came before. The survivors, the niches left open, the lessons written in DNA and sediment. Evolution doesn't erase. It edits. In the wake of the end Permian extinction, the reptiles that would become dinosaurs gained their foothold. In the shadow of the Chicxulub impact, mammals, once small and nocturnal, emerged into the daylight. They filled the forests, they tried new shapes, and in time they climbed, walked, thought. But let's not leap ahead too fast. There's something haunting and humbling in these cascades of cause and effect. How a single variable, a temperature shift, a new molecule, a sudden plume of ash, can unravel entire worlds. Sometimes the cause isn't even visible to the naked eye. Take methane. It's invisible, odourless, and 80 times more potent than carbon dioxide in the short term. Yet when released in large quantities, from melting permafrost or clathrates beneath the sea, it can tip the climate toward chaos. Scientists suspect that methane played a key role in several past warmings, including the Paleocene-Eocene thermal maximum, around 56 million years ago, when temperatures spiked by 5 to 8 degrees Celsius globally in just a few thousand years. During that time, the poles were tropical. Palm trees grew in what is now Alaska. Crocodile-like creatures lounged in the Arctic. It was not an ice-free world, it was a fevered one, and life adapted, but not without loss. Coral reefs suffered. Deep-sea organisms died en masse. Land mammals shrank, likely a response to heat stress and food scarcity. Ecosystems moved, shifted, and collided. And the carbon isotopes in rocks today still carry the signature of that sudden, strange pulse. We often imagine Earth's history as a steady slope. In truth, it's a heartbeat. Pulses of calm and crisis. Building, breaking, rebuilding again. And even now, we live in the rhythm of those pulses. Our climate, our biodiversity, even the shapes of continents are echoes of these past upheavals. Antarctica, for instance, wasn't always frozen. 40 million years ago, it was covered in temperate forests, teeming with ferns and flowering plants. But when plate tectonics pulled it southward and isolated it with the formation of the Drake Passage, ocean currents shifted. The Antarctic Circumpolar Current was born. a barrier of cold water that wrapped the continent in solitude. Temperatures fell, glaciers formed, and the green continent turned white. Again, one change, tectonic drift, set off a cascade, climate, ice, ecosystems, all reshaped by the movement of a continent. You begin to see the pattern, how sensitive the planet is, how interwoven its systems are. Volcanoes influence the sky affects the sea dictates life, and life, in turn, alters the air. We are used to drawing lines between disciplines, geology, biology, chemistry, climate science. But Earth does not recognise those lines. It works as one. And this interconnectedness isn't just ancient, it's present. Right now, we're in what scientists call the sixth mass extinction. It's not triggered by a volcano or an asteroid, but by us, by habitat loss, pollution, invasive species, and above all climate change driven by greenhouse gas emissions. The same carbon that once rose from fissures in Siberia now comes from engines and chimneys. The feedback loops are familiar. Warming melts permafrost. Permafrost releases methane. Methane causes more warming. Forests die, releasing carbon. Oceans absorb more CO2, acidify, and disrupt marine life. It's a pattern we've seen before, but this time it's faster. 10 times faster than the PEM. 100 times faster than some ancient warmings. The tipping points, thresholds beyond which change becomes unstoppable, may already be approaching, or past. But unlike past events, this one is not written in stone. Not yet. Because this time, the trigger isn't a mindless eruption or a rogue rock from space. It's our choices, our industries, our pace. And that means the aftermath, the cascade, can still be softened. We don't yet know how this chapter ends. But we do know what the past can teach us. That Earth changes, always. And that when it does, the consequences ripple through every layer of the planet. Rock, air, water, and life. And that those ripples last, not for decades, but for ages. The thing about Earth is, it remembers, not in the way we do, not with calendars or journals or careful photographs, but in layers, in strata, in fossils pressed like whispers into stone, in isotopes, trace metals, mineral grains no bigger than dust. The planet carries memory in its bones, and if you learn how to read those bones, you begin to see a pattern. Extinction, yes. Upheaval, certainly. But also rhythm, return, evolution dancing with disaster again and again. Because what we think of as stability, forests that rise, oceans that stay put, seasons that follow a polite schedule, that's the exception. The pause, the inhale before the next great shift. Long before the dinosaurs vanished in a storm of fire and dust, long before trilobites scuttled through Cambrian seas, there were other extinctions, other resets, some so total that they nearly erased the story of life altogether. Others more quiet, like a slow unravelling, species disappearing one by one until whole ecosystems gave way to something new. Take the Ordovician extinction, for instance. About 443 million years ago, Earth was a very different place. Most life lived in the oceans. The continents were still scattered and bare, and land plants were just beginning to experiment with mossy footholds. And then, suddenly, temperatures plummeted. Glaciers advanced. Sea levels fell. Shallow marine habitats, where most species lived, vanished almost overnight. Scientists think this may have been triggered by a burst of mountain building. New rock exposed to the air pulled carbon dioxide out of the atmosphere through weathering, cooling the planet. Or perhaps the sun dimmed slightly, or tectonic shifts rearranged ocean currents. The result was a freeze, then a flood, because once the glaciers melted, sea levels rose again. The climate seesawed, and life, unable to adapt fast enough, suffered. more than 80% of marine species disappeared. We see it today in the rock record, in the sudden disappearance of graptolites, in changes to conodont fossils, in layers rich with glacial debris followed by deep black shales, marking low oxygen ocean recovery. Then came the Devonian extinction, around 370 million years ago. This one took longer. It wasn't a single event, but a series of pulses, an unravelling stretched over millions of years. Again, most of the casualties were marine, reef-building organisms, armoured fish, early ammonites. Why? It's still debated. Some point to the evolution of land plants. As roots spread, they broke down rock, releasing nutrients into rivers, which poured into the oceans. The nutrient surge caused algal blooms. The blooms died, sank and rotted, sucking oxygen from the water. Anoxic seas spread. Others blame volcanic activity, or asteroid impacts, or all of the above. It's rarely one thing. Extinction, like climate, is a system. One element knocks into the next. Nutrient cycles, ocean circulation, global temperature, photosynthesis, predation. Everything is connected. Next came the biggest one of all, the end-Permian extinction, the great dying we've already visited. But even that, with its volcanoes and methane and mass collapse, was not the end. Because just 50 million years later, the Earth did it again. This time, at the end of the Triassic, another wave of extinction washed through the biosphere. More volcanoes, more carbon dioxide. This time from the Central Atlantic Magmatic Province, a vast flood basalt event that accompanied the breaking apart of the supercontinent Pangaea. As the Atlantic Ocean began to open, magma surged up through faults and fractures. The gas it released warmed the planet, acidified the oceans, and sent countless species, especially in the seas, into extinction. But among the survivors were the earliest dinosaurs, and in their shadow, mammals. And then, of course, came the one we know best, the end Cretaceous extinction, 66 million years ago, with its asteroid and its winter and its world reset. 5 major mass extinctions, 5 known chapters when the biosphere collapsed and rewrote itself. But they're not alone. Throughout Earth's history there have been dozens, even hundreds, of smaller die-offs, pulses of change, regional collapses, global near misses, moments when the planet could have turned a different way. And among all of them, one thread remains. Life always returns. But never quite the same. What's most astonishing isn't just that life survives, but how it evolves in the aftermath. After the Ordovician extinction, new types of fish appeared. Jawed ones, better swimmers, more versatile. The Devonian collapse cleared the stage for the rise of tetrapods, 4-limbed vertebrates who would eventually crawl onto land. After the Permian, reptiles took centre stage, their sprawling gaits and scaly skins better suited to the hotter, drier world. And after the Cretaceous, when dinosaurs fell silent, mammals emerged into the gaps. The age of mammals wasn't preordained, it was an accident of survival, and that pattern, disaster followed by opportunity, is written across every evolutionary leap. The first eukaryotes, the first shells, the first eyes, the first limbs, wings, flowers, feathers. Every breakthrough came in the wake of a shake-up. The Cambrian explosion, often celebrated as life's big debut, came after one of the most extreme ice ages in Earth's history. A Snowball Earth event that may have scoured the biosphere down to the microbial. And then, in the wake of that chill, evolution ignited. Hard shells, specialized limbs, complex body plans, predators and prey, ecosystems. It's almost as if Earth's greatest creativity follows its deepest crises. And the cause is not just death, but vacancy. Extinction opens ecological niches. When a predator disappears, prey can expand. When corals vanish, other reef builders take their place. Forests fall and grasses spread. The The survivors adapt, radiate, experiment, and the tree of life branches in new directions. You can see it in the fossil record, a lull, a break, a silence, then a surge. A bloom of new forms, unfamiliar but wondrous. There's something deeply human in that idea, that from loss something unexpected might grow. That destruction isn't the end of the story, just the turning of a page. But it's important to remember the cost is high. Mass extinctions aren't tidy. They leave behind shattered systems, empty landscapes, disrupted cycles. Recovery can take millions, even tens of millions of years. And some branches of life never return. Trilobites never came back. Nor did the rugose corals, the ammonites, the flying reptiles. Evolution doesn't rewind. It writes new lines. And as we face our own moment of planetary stress, the parallels become harder to ignore. We see carbon dioxide rising faster than in any past event. We see species disappearing at rates that rival past collapses. We see coral reefs bleaching, rainforests burning, glaciers vanishing, sea levels creeping. We know these signs. We've read them in stone. The Earth has been here before, not with cities and satellites, but with carbon spikes, warming oceans, anoxic zones. We know what happens next, not from theory, but from history. And yet, this time is different, because this time we know it's happening. This time we have the tools to measure, to model, to understand. This time the asteroid is us, but also, maybe, the answer is too. Because while Earth teaches us that change is inevitable, it also shows us that the shape of change matters. Its speed, its scope, its triggers, its buffers. Life survived every previous extinction not by doing nothing, but by adapting, by shifting in response to stress. And if we are part of life, not separate from it, but a continuation of that same thread, then we too must adapt. Our ancestors did. They survived the Toba eruption, which darkened the skies. They crossed ice bridges, fled deserts, outlasted droughts, and in each case they didn't just endure, they innovated language, fire, farming, storytelling. Now, our challenge is not to survive extinction, but to prevent one, or at least, to soften the fall, to break the cascade before it completes the loop, to learn from a planet that has given us every clue, if only we'll listen. Because the Earth's memory is long, but our moment in it, this one, is short, and beautiful, and still being written. In the long story of Earth, humans arrive late. Not in the last chapter, but the last paragraph. The final sentence trailing behind billions of years of tectonic drama and biochemical invention. We showed up to a planet already rich with stories, and from the moment we began to listen, we've tried to understand what came before. Maybe it started with a rock that looked out of place, a shell found inland, a strange shape embedded in stone, something that didn't belong, or rather, something that once did but no longer could. A fossil. Fossils were among the earliest clues. Long before we had radiometric dating or plate tectonics or atmospheric models, people found teeth the size of fists and bones that curved like serpents through the earth. They imagined dragons, giants, lost worlds, and in a way they weren't wrong. They were feeling the edges of a truth they didn't yet have words for, that the ground beneath them held memory. And slowly, over centuries, the language began to form. In the 17th century, a Danish scientist named Nicholas Steno noticed something simple but profound, that layers of rock are deposited over time, with the oldest at the bottom and the youngest on top, unless something has disturbed them. This principle, known as superposition, became a cornerstone of geology. It meant that the Earth could be read like a book, not all at once and not always clearly, but line by line, layer by layer. Then came James Hutton, in 18th century Scotland, walking the craggy coastlines and riverbanks, peering at tilted strata and puzzling over their shape. Where others saw disorder, Hutton saw deep time. He realised that rocks could be eroded, buried, melted and lifted again, a cycle without end. In 1788, standing at Siccar Point, where vertical layers of ancient rock met horizontal bands above them, Hutton uttered one of geology's most famous phrases: "No vestige of a beginning, no prospect of an end." It was a radical idea. That Earth was not thousands of years old as tradition claimed, but millions, maybe more. Time enough for mountains to rise and fall, oceans to appear and vanish, species to bloom and disappear without ever meeting the human eye. And if time was that vast, how much had we missed? As the 19th century unfolded, curiosity bloomed. Fossil hunters scoured cliffs and quarries, their hands stained with chalk and shale. Mary Anning, a self-taught fossil collector on the coast of Lyme Regis in England, uncovered ichthyosaurs and plesiosaurs from the Jurassic sea cliffs. Her work, often overlooked in her lifetime, would later help transform paleontology and the image of what life once looked like. At the same time, the rocks themselves began to speak in a new language: chemistry. Scientists learned that elements decay at predictable rates. Uranium becomes lead. Potassium becomes argon. These changes act as clocks, not ones you can see or hear, but atomic timers buried in mineral crystals. With careful measurement, geologists began to assign dates to the layers. Not guesses, but numbers. Billions. Hundreds of millions. The scale of Earth's history snapped into sharper focus, and with those numbers came context. The Cambrian explosion, around 540 million years ago, the Permian extinction, about 252 million, the asteroid that ended the dinosaurs, 66 million. Suddenly, time had structure. It wasn't just deep, it was specific, and with every new tool, the map of Earth's past became more detailed. Charles Lyell, with his principles of geology, argued that the processes shaping the Earth today, erosion, sedimentation, volcanic activity, were the same ones that shaped it in the past. This idea, uniformitarianism, gave geologists a kind of time machine. If you understood rivers and cliffs today, you could imagine their ancient ancestors. And Darwin, aboard the Beagle, carried Lyell's book with him. He used its ideas to frame his theory of evolution, not just of animals, but of Earth itself. Geology, biology, and time were beginning to interlace. And then, in the 20th century, came a quiet revolution that would change everything: plate tectonics. For centuries, the fit of the continents had been noticed, how South America and Africa seemed to lock together like puzzle pieces, but it wasn't until scientists began studying the ocean floor and detecting patterns in magnetic minerals that the truth emerged. The Earth's crust is divided into plates that move. They drift, they collide, they pull apart, and when they do, they shape mountains, birth volcanoes, open oceans. Suddenly everything made more sense. Why earthquakes clustered along certain boundaries, why fossils of the same animal appeared on distant continents, why mountain ranges curved like waves frozen in stone. The Earth was alive in a new way, not just in its life forms, but in its very skin. And with that knowledge came a new generation of seekers. In the 1960s, on a hillside in Italy, a geologist named Walter Alvarez was studying a peculiar layer of clay. It was thin, no more than a few centimetres, but it marked something profound, the boundary between two ages. Below the clay, rocks were full of Cretaceous fossils, ammonites, foraminifera, signs of a rich marine world. Above it, they were gone. What happened in that thin layer? With the help of his father, a Nobel Prize-winning physicist, Alvarez analysed the clay for rare elements. What they found was startling. An unusually high concentration of iridium, a metal rare on Earth, but common in asteroids. This clay, it seemed, was not just a mark of time. It was a signature, a scar. The impact theory of the dinosaur extinction was born, not in a blast crater or a fossil bed, but in a quiet seam of Italian rock. Soon, that layer was found all over the world. The same iridium spike, the same silence in the fossils, and eventually scientists identified the crater buried beneath the Yucatan Peninsula, a circular wound over 180 kilometers wide, Chicxulub. And suddenly, a story that had once sounded like science fiction, an asteroid ending an era, became history. Stories like this are everywhere, if you know how to look. In South Africa, in the Barberton Greenstone Belt, geologists hike among some of the oldest rocks on the planet, more than 3.5 billion years old. They're not much to look at, weathered and folded, but inside them are chemical signatures of early oceans, layers rich in iron, trace fossils of microbial mats. Some researchers believe they even preserve raindrop imprints, tiny dents left when ancient showers hit warm volcanic ash. Elsewhere, in Western Australia, tiny zircon crystals, no larger than a grain of sand, have been found embedded in younger rocks. These zircons are the oldest known pieces of Earth's crust, over 4.4 billion years old. And inside them, isotopic signatures suggest something shocking, that liquid water may have existed on Earth just 150 million years after it formed. That discovery didn't come with fanfare. It came from careful lab work, from isotope ratios, from patience. The story of Earth is not just one of collisions and extinctions, but of quiet persistence, of scientists kneeling in dirt, squinting at specks, asking questions no one has asked before, and sometimes those questions take a lifetime to answer. In the Canadian Arctic, paleontologists dig into frozen ground, seeking clues about ancient climates. Trapped in permafrost are ancient pollen grains, insect wings and spores, all sealed in time. From these, we learn how ecosystem responded to previous warmings and coolings, how trees migrated, how ice expanded and shrank. In Greenland, glaciologists drill deep cores through layers of ice, pulling up cylinders that read like diaries. Each layer captures a year, dust from deserts, ash from volcanoes, bubbles of ancient air, tiny time capsules, each one holding the atmosphere's breath. From these, we learn how carbon dioxide has waxed and waned, how temperatures have fluctuated, how quickly the planet can shift. In deep ocean trenches, marine geologists use remotely operated vehicles to map hydrothermal vents, the same environments where life may have begun. They collect microbes that feed on sulfur, survive without sunlight, and hold enzymes with strange, promising properties, some that might help us understand alien life, or craft new medicines, or simply reveal how life works under pressure. In deserts, planetary geologists study dried lake beds and dust devils, not just for what they tell us about Earth, but for what they might tell us about Mars. Many of the tools and techniques used to decode our planet's past now guide our search for ancient environments on other worlds. And behind every sample, every data point, every published paper, there's a person, often sunburned, often sleep-deprived, often uncertain. Science is not a steady climb. It's not a line from question to answer. It loops, it doubles back, it hesitates, it gets lost in detail, in error, in doubt, and then, sometimes, it emerges, blinking, surprised into clarity. One of the most important revolutions in understanding Earth's history came from noticing the magnetic orientation of tiny crystals in basalt. In the mid-20th century, scientists measuring the seafloor noticed something strange. Bands of rock with reversed magnetic polarity, mirrored on either side of the mid-ocean ridges. It meant that new crust was being created at these ridges and spreading outward, pushing continents apart. This quiet data, just magnetism, confirmed the theory of plate tectonics, and with it, rewrote our understanding of earthquakes, mountains, oceans, even the shape of the planet itself. And it didn't come from a single eureka moment. It came from hundreds of scientists, ships braving storms, instruments bobbing in the water, notes scribbled in logbooks, Progress, pulled slowly from the deep. And this is the rhythm of discovery. Some of the most important work isn't glamorous. It's sorting through fossils the size of rice grains, measuring the carbon content of a rock for the 5th time, trying to make sense of messy, contradictory data, revisiting the same cliff face year after year because one layer doesn't behave the way it should. And sometimes a mystery sits unanswered for decades. Not because no one cares, but because the tools don't exist yet. The technology needs to catch up, the funding, the insight, and then one day, a new method, a new satellite, a new algorithm. And suddenly, that old question flickers to life again. There's a certain kind of magic in that. Because geology, like astronomy, like biology, is not just about rocks or stars or species. It's about wonder, about patience, about returning to the same question again and again, hoping it will answer differently this time. And in that way, scientists are storytellers. They take the raw material of the Earth, the ash, the ice, the iron, the fossils, and they weave it into narrative. They explain how continents moved, how creatures vanished, how skies changed. They bring clarity to chaos. They make meaning from mineral, and perhaps more importantly, they remind us that the story of Earth is still unfolding. We're not just readers of this tale. We're now part of it. Our cities, our emissions, our choices. We have become a geologic force. And the future geologists, 100, 1,000, 10,000 years from now, they will dig through our layers. They'll find our plastic, our soot, our bones, and they'll ask, as we do now, what happened here? And maybe they'll also ask, who were these people? What did they understand? What did they change? And what, in the end, did they leave behind? If stories are the soul of science, then data is its breath. And in the story of Earth, a story billions of years long, the data is buried deep, often invisible, sometimes microscopic, and always waiting. This is the realm of the deep science dive. Not dramatic explosions or cinematic discoveries, but the quiet, steady precision that makes everything else possible. The tools behind the timeline, the math behind the metaphor, the chemistry inside the stone, and it begins with the atom, specifically the unstable ones. On a quiet bench in a geochemistry lab, a tiny mineral sample, perhaps zircon no larger than a grain of sand, is prepared for analysis. It's been ground, polished, washed, etched. Inside it, locked in its crystalline lattice, are atoms of uranium. Uranium over time transforms. Its nucleus is unstable. It decays step by step into lead, predictably, reliably, at a pace unaffected by heat or pressure or time itself. And by measuring how much uranium remains and how much lead has formed, scientists can calculate how long the mineral has existed. This is radiometric dating. Not a single method, but a family of techniques: uranium lead, potassium argon, rubidium strontium, carbon-14, each tuned to a different age range, each useful for a different kind of material. Carbon-14, for example, is ideal for dating once-living things: plants, bones, cloth, charcoal, up to about 50,000 years old. Beyond that, the signal fades, like an echo lost in the canyon. For older samples, rocks, meteorites, the Earth itself, other isotopes take the stage. Uranium-lead dating can reach back billions of years, and it's how we know the age of the oldest minerals on the planet. These methods are not simple. They require clean labs, sensitive instruments, and careful calibration. Contamination can throw everything off. One misplaced fingerprint, one fleck of dust, one tiny bubble in the resin, and the entire analysis may become noise. But when it works, it gives us not just numbers, but context. Those 4.4 billion-year-old zircons from Australia, their isotope ratio suggests not only age, but temperature. From them, we infer the presence of liquid water. They tell us about early crust, early oceans, early conditions, all from a sliver of crystal smaller than the tip of a pencil. This is the beauty of isotope geochemistry. It reads not only the clock but the climate. Oxygen isotopes, for instance, can reveal temperature. Lighter and heavier oxygen atoms behave slightly differently in evaporation and condensation. By measuring the ratio of oxygen 16 to oxygen 18 in ice cores, shells, or minerals, scientists can reconstruct ancient temperatures, year by year, layer by layer, going back hundreds of thousands of years. Carbon isotopes tell another story. Carbon-12 is the more common isotope, but life prefers it. Living things, plants, plankton, animals, tend to absorb more carbon-12 than carbon-13. So when a mass extinction occurs and life suddenly vanishes, the ratio in sediments shifts. It's like a pulse monitor on the biosphere. A sharp drop can signal a collapse. A rebound may hint at recovery. Sulfur isotopes too leave their mark, often during periods of low oxygen. When sulfur-cycling bacteria become dominant, they leave behind isotope signatures that speak of anoxic oceans, microbial blooms, and sulphurous skies. Taken together, these isotopes are like threads woven into the fabric of rock, and when read with care they reveal not just age but environment, not just what happened, but how. But to truly understand ancient life, we need more than chemistry. We need fossils. And fossils, it turns out, are far more varied and fragile than the dramatic skeletons in museums might suggest. There are the obvious ones: bones, teeth, shells, hard parts that resist decay, that mineralize over time, that survive erosion and burial. These are the fossils that define periods: trilobites, ammonites, dinosaur femurs and mammoth tusks. But there are also the soft ones: impressions in mud, microbial mats, leaves pressed into silt. Some preserve the fine structure of feathers, others record the movement of an animal, a footprint, a burrow, a coprolite. Even the shadow of a jellyfish caught in a moment, trapped for eternity. In the Burgess Shale of Canada and similar sites around the world, paleontologists have uncovered entire communities from the Cambrian period. Creatures with no modern analogue, their soft tissues preserved in exquisite detail. They show us not just who lived, but how they lived, what they ate, how they moved, what shaped their world. And in places like China's Yunnan province or Germany's Solnhofen limestone, fossils preserve colours, behaviours, even melanosomes, pigment structures that hint at the patterns and hues of ancient feathers. Paleobiology, the study of ancient life, is no longer just about what species existed. It's about ecosystems, food webs, evolution, extinction. And increasingly, it overlaps with genomics, because sometimes evolution leaves behind more than bones. In the genomes of living organisms, we find echoes of the past, genes inherited from ancient ancestors, sequences shared across vast evolutionary distances, the gene that allows birds to form beaks, the one that gives whales vestigial hips, the ancient toolkit of Hox's genes that tells embryos where to grow arms, legs, wings, fins. And by comparing genomes across species, across time, scientists can infer the branching paths of life, the timing of divergences, the history written in DNA. Some even search for signs of horizontal gene transfer, moments when genes jumped across species, often via viruses, leaving behind strange mosaics of ancestry. A bit of jellyfish in a clam, a bacterial gene in a plant. The lines blur, and in the oldest lineages, extremophiles, archaea, thermophilic bacteria, researchers look for clues to life's earliest adaptations. How did the first cells survive? What enzymes did they use? Were they born in vents, in clays, in ice? These questions bleed into astrobiology, the study of life not just on Earth, but anywhere. And to explore them, scientists recreate ancient conditions. They build simulation chambers, replicate hydrothermal vents, mix gases and UV light in glass domes. They test whether RNA can self-replicate, whether lipid membranes can form in brine, whether amino acids can survive the radiation of space. Some go further. They send instruments to Mars, to Europa, to Enceladus. They peer into exoplanet atmospheres searching for biosignatures, methane, oxygen, water vapour, spectral fingerprints of possible life, and always they use Earth as their guide. Because our planet, in all its chaos and creativity, is still the only template we have. If ancient rocks and isotopes tell us where we've been, then models, strange, beautiful mathematical models, help us understand how we got there, and maybe where we're going next. Because even the deepest fossil bed only captures a moment, a slice, a shadow. What we often want and need is motion, change over time, the slow dance of continents, the rise and fall of sea levels, the expansion of ice sheets, the ripple of warming across a hemisphere. We want to rewind the planet, to watch it breathe, and to do that, we build simulations. Climate models are among the most complex tools humans have ever made. They don't just simulate weather, though they do that too. They simulate entire Earth systems. Atmospheric circulation, ocean currents, cloud formation, carbon cycles, glacial advance, soil moisture, volcanic emissions, solar variation, even sometimes vegetation growth and animal migrations. They're built from physics, fluid dynamics, thermodynamics, radiative transfer equations, and they're layered with data, satellite records, ice core measurements, tree rings, sediment cores, fossil pollen, coral bands, isotope ratios. Some are run on supercomputers the size of buildings. Others are simplified versions designed to test a single variable. What happens if we add more volcanic ash? What if the ice sheet collapses? What if the Earth's orbit wobbles just slightly? Because yes, the Earth's orbit wobbles. Milankovitch cycles, they're called. A subtle interplay of eccentricity, how stretched Earth's orbit is, obliquity, the tilt of Earth's axis, and precession, the slow wobble of that tilt. Over tens to hundreds of thousands of years, these cycles change how sunlight is distributed across the globe, and that, in turn, helps trigger ice ages and warm periods. We've seen it in the data. Glacial periods match orbital patterns. Warm interglacials, like the one we're in now, correspond to solar intensity in the northern hemisphere. It's not the only factor, but it's a powerful metronome in Earth's long climate rhythm. And when scientists plug these cycles into models, the results line up. Ice sheets grow and shrink, sea levels rise and fall, deserts advance and retreat. It's like watching the planet breathe in slow motion. But there's more. Some models go back even further, to the deep time of the Paleozoic and Mesozoic eras. They reconstruct ancient Earths with different coastlines, different mountain ranges, different oxygen levels, and they ask, what was the weather like when trilobites ruled the sea? When ferns formed vast coal swamps? When pterosaurs soared above warm, shallow seas? To do this, researchers use paleogeographic reconstructions, maps of ancient continents built from tectonic evidence, fossil distributions and magnetic signatures locked in rock. They feed these maps into models. They adjust the atmosphere to match ancient compositions, and then they watch. Rain falls in Gondwana, winds swirl over the Tethys Sea, monsoons batter the edge of Laurasia, deserts form, rivers shift, and bit by bit the ancient world reassembles itself. These aren't guesses, they're experiments, and the predictions they make can be tested against sediment types, against fossil distributions, against oxygen isotopes in conodont teeth, even against growth rings in fossil wood. Sometimes the models surprise us. They show that the Sahara wasn't always a desert. Just 6,000 years ago it was green, a land of lakes and grasslands dotted with human settlements. This green Sahara was caused by a slight change in Earth's tilt and orbit, strengthening monsoon rains, and as the orbit shifted again, the rains receded, the lakes dried, and the desert returned. Models also help us understand extinction. Why did the end Permian extinction hit marine life so hard? Climate models suggest ocean temperatures rose dramatically, reducing oxygen. Combine that with sluggish circulation and volcanic carbon emissions, and you get an ocean both hot and breathless. Life suffocated. Models show how the asteroid that ended the dinosaurs may have triggered global winter, not from the impact itself, but from the sulfur aerosols it kicked into the stratosphere. Sunlight blocked, photosynthesis halted, food chains unravelled. And these models aren't just academic. The same physics, the same equations, the same principles, they're the ones used to model today's climate. The same tools that tell us about Snowball Earth and hothouse climates now show us how carbon dioxide from cars and factories is warming the atmosphere, altering rainfall, melting ice. And the parallels are striking. Past climate events like the Paleocene-Eocene thermal maximum saw global temperatures rise by 5 to 8 degrees over thousands of years. Today, we're on track for a similar rise in just centuries, or less. Faster than forests can migrate, faster than reefs can adapt, faster than many species can evolve. And so scientists model future climates too. They run scenarios, high emissions, low emissions, carbon neutral by 2050, business as usual, and each one paints a different picture. In some, the Amazon becomes a savanna, the Arctic becomes seasonally ice-free, coastal cities flood, weather grows more extreme, food systems strain. In others, with strong action, the planet stabilizes, the damage slows, ecosystems adapt. The future narrows back toward balance. None of the models claim certainty. They are tools, not oracles. But they give us something rare: foresight, a glimpse of what might come, and a chance, however slim, to prepare. But modelling doesn't stop at the surface. Scientists model Earth's interior too, how heat moves through their mantle, how plumes of magma rise, how tectonic plates interact. They simulate earthquakes, magma chambers, even the growth of continental crust. They ask why the Earth has a magnetic field, and why sometimes it reverses. They model impact craters, calculating how shockwaves travel through rock, how ejecta blankets fall, how long it takes for ecosystems to recover. They model the origin of the moon, testing different angles and speeds for the Theia impact, watching debris swirl, coalesce, settle into orbit. They model the cooling of the early Earth, the differentiation of its layers, the rise of its oceans. They even model abiogenesis, the origin of life, using chemistry, probability, and computer simulations to test which molecules might form under which conditions and how long it might take for order to emerge from chaos. And with each model, the question isn't just what happened, it's how. How does a planet evolve? How does life begin? How do climates tip? How do oceans change? How does the world rebuild? And in that process, that asking, science becomes something more than just knowledge. It becomes empathy, a way of imagining not just what the Earth is, but what it feels. We simulate the winds not just to track storms, but to understand the patterns of the sky. We model magma not just to predict eruptions, but to grasp the pulse of the deep. We run ancient oceans on computers not just to watch them flow, but to imagine what it was like to be there, beneath the waves, in the heat, before the world had trees or eyes or names. Because science, at its core, is an act of imagination, an act of listening. And when we dive deep, into isotopes, into genomes, into equations and chaos and code, we are not moving away from wonder. We are circling closer to it, closer to the moment the first cell divided, closer to the breath of a mammoth in the snow, closer to the sound of rain falling on a newborn continent, and closer perhaps to understanding our place in it all, not as masters, not as passengers, but as part of the same long patient system, the same story still unfolding. When the world ends, it doesn't end all at once, not even in the face of fire or ice or silence. Mass extinction is not a door slammed shut, but a long and aching quiet. The end comes slowly, unevenly, in ripples and delays. A forest doesn't vanish overnight. It thins, weakens, forgets how to return in spring. An ocean doesn't die with a single bloom. It gasps layer by layer until light no longer finds its way. And just as the collapse is slow, so is the recovery. Because evolution doesn't rebuild what was lost. It builds what can survive next. After the asteroid struck 66 million years ago, the dinosaurs didn't vanish instantly. Some died in the blast, yes, crushed or vaporized. Others in the tsunamis, the earthquakes, the fires. But many, perhaps most, died in the days, months and years that followed. Starvation, freezing, poisoned skies, disrupted food chains, slow attrition in a world that no longer made sense. The same is true in the oceans. Planktonic algae, the base of the food web, collapsed. Without them, filter feeders starved. Predators followed. Coral reefs, already fragile, became graveyards. Ammonites disappeared forever. Mosasaurs, plesiosaurs, ichthyosaurs, gone. But in the ashes, something stirred. The survivors were small, adaptable, generalists. Mammals hiding in burrows, birds sheltering in the canopies of scorched trees, fish with broad diets, scavengers, opportunists, those who could live in the cracks of a broken world. And over millions of years, those survivors changed. Forests returned, not the same species, not the same rhythms, but green nonetheless. Mammals grew larger, explored new niches. Primates emerged, climbing through the regrown canopies. Whales, once landbound, returned to the sea. Grasses spread, hoofed animals ran, and eventually, under the African sun, a lineage of apes began to walk. But recovery wasn't fast. It took 10 million years for biodiversity to reach pre-extinction levels. 10 million years of experimenting, diverging, testing what the planet could now support. The rules had changed. The climate was different. The continents had shifted. The chemistry of the atmosphere had subtly rearranged itself. Every extinction rewrites the terms of life. After the Permian extinction, when 90% of species disappeared, it took even longer. Ecosystems were shattered. Entire modes of life were extinguished. Reef ecosystems, for example, took nearly 100 million years to fully recover. The ones that returned weren't built by the same organisms. New architects took their place, scleractinian corals instead of ancient sponges and stromatoporoids. And on land, the dominance of synapsid reptiles, our distant relatives, gave way to the rise of the archosaurs, the lineage that would lead to crocodiles, pterosaurs, and of course dinosaurs. The Permian didn't just erase life, it tilted the board, and evolution played out along a new path. Sometimes, recovery doesn't mean return, it means reinvention. After the Ordovician extinction, it wasn't just marine life that bounced back. The next big evolutionary wave brought more complex food chains, predators with jaws, more active swimmers, more defensive shells. The world had changed, and so had the rules of survival. And after the Devonian extinction, which hit reef systems hard, it was plants that began to push further inland. Deep-rooted trees evolved, soils thickened, the land grew more hospitable to animals, amphibians became tetrapods, lungs replaced gills, and the stage was quietly set for vertebrates to leave the water behind. What these long recoveries reveal is not just the resilience of life, but the plasticity of evolution, the ability to reroute, to adapt not only to hardship but to absence, and sometimes what emerges is stranger than what was lost. After the Triassic extinction, the early dinosaurs, small, fast, bird-like, began to expand into niches left empty by their reptilian cousins. Within just a few million years, they diversified into towering herbivores, sharp-toothed predators, horned browsers, and feathered gliders. From scarcity came proliferation. This pattern repeats. In the wake of destruction, ecosystems regrow, but rarely symmetrically. Some places recover faster, typically the tropics, where energy and sunlight are abundant. Others, like polar regions, may take longer. Biodiversity doesn't rise in a smooth curve, but in pulses, surges of innovation followed by plateaus, extinctions, and new surges. And as life returns, so does geology. Carbon, once trapped in living matter, returns to rock. Chalk cliffs, coral reefs, coal seams, all are the sedimentary ghosts of recovery. Volcanic activity calms. Erosion shapes new landscapes. Rivers find new paths. Glaciers retreat or advance. The skin of the Earth reshapes itself to suit the new world. And through it all, the biosphere learns. Not in any conscious sense, but in pattern. The oxygenation of the atmosphere, for example, was not a one-time event. It came in pulses. The first great oxidation event occurred over 2 billion years ago, driven by cyanobacteria, the planet's first photosynthesizers. They exhaled oxygen into a world unprepared for it. And that oxygen, toxic to many early life forms, triggered one of the planet's earliest mass extinctions. But oxygen didn't rise smoothly. It fluctuated for hundreds of millions of years. Mini-oxygen spikes, then crashes, slow climbs, plateaus. It took nearly 2 billion years more before atmospheric oxygen reached levels similar to today, enough to support large animals, high metabolism, brains. In that long gap, Earth was experimenting. Sometimes oxygen supported life, sometimes it burned it away. Life adapted, evolved new enzymes, new metabolisms, mitochondria, muscles. This is what recovery looks like on a planetary scale, not a reset but an unfolding, a test of what life the Earth can now sustain, and it leaves lasting consequences. After every major extinction, the composition of the atmosphere changes, often subtly. Greenhouse gases rise or fall, methane spikes fade, carbon cycles adjust, volcanic emissions taper off, the balance takes time to re-establish. And that new balance affects climate, ocean chemistry, rainfall, even the distribution of land plants. Recovery is not separate from climate. It is entwined with it. And in turn, the recovering biosphere shapes the climate again. Trees absorb carbon. Algae fix nitrogen. Coral reefs alter local temperatures. The planet is not a stage upon which life performs. It's a partner, a co-author. This becomes especially clear in the story of the Cenozoic, the era we're living in now. After the asteroid cleared the skies, mammals rose, grasslands spread, new herbivores grazed, and in their wake came predators, cats, dogs, raptors, early hominids. Ice ages arrived and retreated, mountains uplifted, river systems changed, the Sahara dried, sea levels rose and fell more than 120 meters, again and again. And then one species began to paint caves, to bury its dead, to shape stone into tools. Us. Our species is not separate from the Earth's recovery. We are part of it. We are the product of extinction and rebound, of scarcity and adaptation. Our bodies carry the blueprints of ancient vertebrates. Our lungs still echo with the oxygen rise of the Proterozoic. Our blood carries the salt ratios of long-lost seas. Our sleep follows lunar cycles. Our bones remember gravity. But now, the pace is shifting. Recovery, once measured in millions of years, must now contend with human time. And what we're seeing is that recovery, even in our brief span, is slow. Forests cut down in decades take centuries to return. Coral reefs bleached in summers may need millennia. Species lost do not reappear. Rivers dammed and rerouted shift whole ecosystems. The scars remain. And yet, there is still motion. The return of wolves to Yellowstone rewrote the landscape. Not metaphorically, but literally. They changed the movement of deer, which allowed forests to regrow, which stabilized riverbanks, which altered erosion, which changed the river's path. The system relearned itself. This is the hopeful part. Life does not forget how to rebuild, but it needs time and space and silence, and that time is what we often deny it. The recovery from past extinctions tells us that 10 million years is fast, 30 is average, 100 is not unusual. By that scale, human civilization has barely existed at all. So the question becomes, what kind of world are we shaping? Not just for us or our children, but for whatever comes next. Because recovery will happen. The planet will endure. The biosphere will find a way. It always has. But what it becomes depends on what we leave behind, what survives, what seeds remain in the soil, in the sea, in the genome. In that sense, our footprint is not just carbon, it's evolutionary. We are not the first species to change the world. Cyanobacteria did it with oxygen, plants did it with roots, trilobites did it by burrowing, but we are the first to know that we're doing it. And that knowledge changes everything, because with it comes a kind of responsibility. Not to stop change. Change is inevitable, but to shape it wisely. To listen to the past not as a warning but as a teacher. Recovery is possible, but it requires time, and time is what we still have, for now. Stand outside sometime barefoot. Feel the ground under your feet, the quiet solidity of it, the cool breath of wind on skin, the sun on your eyelids even when closed. It's easy to forget that all of this, the weather, the soil, the rhythm of days, is temporary, that it wasn't always this way, and that it won't always be. Because the earth has never stood still. It has frozen solid. It has melted to the core. It has been hit, shattered, drowned, burned and rebuilt. 5 times life nearly vanished. 5 times the world emptied its shelves, wiped its slate. And each time, slowly, shakily, life returned. Never in quite the same shape. And now, we are living through a new shift. But this time, it's not an asteroid. Not a volcano. Not the wobble of an orbit or the twitch of a solar cycle. This time the pressure comes from within, from us, from fire drawn from stone, from carbon ripped from the bones of ancient swamps and set loose into the sky, from forests felled, oceans warmed, species scattered. This time we are the trigger, and this time we are aware. That may be the most astonishing fact of all. Not the damage, though it's vast, but the consciousness of it. No trilobite ever worried about extinction. No fern mourned the Devonian die-off, but we know, we measure, we model, we debate, we hope. And hope, fragile as it is, makes a difference, because knowledge carries weight. When you know the depth of time, the long arc of cause and effect, the patient stitching of ecosystems, you begin to see yourself differently. Not as separate, but as embedded. Not a visitor, but a continuation. We are made of earth. Not just metaphorically, but atom by atom. The calcium in our bones forged in dying stars. The oxygen in our lungs a gift from cyanobacteria. The iron in our blood a relic of a molten core. We are geology, animated, biology, thinking, chemistry, dreaming. And yet, for all our cleverness, we're also clumsy. We push too hard, take too much, trust that the planet will absorb our urgency. And sometimes it does. Rain still falls, trees still leaf, birds still migrate. But the signs are harder to ignore. Winters that don't quite freeze, rivers that no longer reach the sea, glaciers thinned to glass, coral reefs pale as ghosts, migrations misaligned, seasons confused. The world is whispering back, and its voice is growing strained. We have entered what scientists call the Anthropocene, a proposed new epoch marked not by asteroid or ice, but by human activity. It is an age defined by plastic in the deep sea, by soot in glacier cores, by the bones of domestic animals outnumbering all wild mammals combined. And unlike the epochs before it, this one knows its name. That awareness is both a burden and a beacon. Because if we are capable of altering the planet, its atmosphere, its oceans, its rhythms, then we are also capable of choice. Not perfect control, not reversal, but change. And change, the Earth reminds us, is not inherently bad. Some of its most beautiful moments have come after upheaval. Forest from ash, reefs from ruin, flight from extinction. Life doesn't resist change. It flows through it. The danger isn't change itself. The danger is speed. When carbon levels shift slowly, ecosystems adapt. Corals move. Species migrate. Ice ebbs. Trees inch uphill. But when the change comes fast, faster than in any known moment in geological history, life struggles to keep up. Mismatches appear. Tipping points loom. And so we are left in a narrow window, wide enough for hope, but closing. We can slow the burn, bend the curve, make room for recovery. We can plant, protect, restore. We can listen to the past, not as prophecy, but as guide. Because Earth has already taught us everything we need to know. It has shown us the cost of imbalance, the patience of recovery, the resilience of small things, and the power of memory. Memory is not just for scientists, it lives in stories, in language, in the names we give rivers, mountains, winds, in the way farmers read clouds, in how children watch the moon, in ceremony, in song, in stillness. And maybe that's where the answers lie. Not in a single solution, but in remembering what kind of animal we are. We are pattern makers. We are caretakers. We are descendants of survivors. Every one of us carries a lineage that passed through ice ages and deserts, through famine and fire. We are adapted for attention, for curiosity, for care. We are, after all, the species that stayed up late wondering how the world began. And we are still wondering, what will come next? What kind of planet will we leave? What kind of ancestors will we be? We don't need to solve the Earth. It's not a problem. It's a partner. It doesn't need saving. It needs space, stability, respect. It needs us to remember how to live in time, not just in hours and days, but in cycles, in seasons, in centuries, in patience. This is not a bedtime story, though it can soothe. It's a wakefulness story, a reminder that our place on this planet is not fixed. It is shaped by our choices, by what we grow, by what we protect, by what we let go. We are not the conclusion of Earth's story. We are a turning point, and maybe, just maybe, we are the first species to write its next chapter with full awareness of what came before and what could still come after. So here we are, at the end of a very long beginning. We've drifted through magma and microbes, oceans and orbits, collisions and recoveries. We've stood beside the scientists tracing ash through stone, listened to ancient atoms ticking softly in the dark, watched continents drift past each other like slow, sleeping whales. We've seen life fall and return, and through it all, the Earth has turned, quietly, patiently, endlessly, and so have you. Thank you for spending this time with me. Whether you're still fully awake, or somewhere between thought and dream, where metaphors melt and time gets soft around the edges. Thank you for listening, for wondering, for being part of this small shared story. If you found comfort here, if this rhythm, this voice, this journey helped you ease your mind, helped you rest, helped you feel a little more connected to the ground beneath you, I invite you to join us again. You can like or subscribe Or leave a thought in the comments below. Your voice matters here. And if there's a story you'd like to hear, a question about the Earth, or time, or life itself, let me know. This channel exists not to teach, but to wonder alongside you. Next time, we might explore the deep oceans, or the language of trees, or what happens to a mountain after it's born. But for now, let the questions fade. Let the noise soften. Let the rhythm of this planet, this ancient, beautiful, unfinished Earth, hold you. Good night from Just About Earth. And wherever you are in time, sleep well.